Good morning, everyone. I'm a fourth-year PhD student in the Mechanical Engineering Department working with Professor Rohit Karnik. And in collaboration with Amy Smith and her team from D-Lab, we are working on the development of water filters using plant xylem. So access to safe drinking water is a huge problem across the globe. And 80% of the illnesses in the developing world are because of unsafe drinking water. And as you can see from this graph, the majority of the burden of this disease is in the areas of Africa and Southeast Asia. Household water treatment is expected to go a long way towards solving this problem. And in fact, there are several methods and technologies that are currently in place. And some of the ones that are most commonly used in the low-income and the middle-income groups include boiling, solar disinfection, filtration, and chlorination, and straining also. So now, despite the availability of several of these methods, none of them except boiling has managed to really achieve scale at a global level. And some of the key barriers include, first of all, awareness about the importance of safe drinking water. Second is access to these technologies. Third is affordability. And finally, social acceptance. So there still continues to be a need to develop more products that are either more suited to user needs or find methods of increasing the uptake of existing technologies. So if we look towards nature for inspiration, then we find that there is a potential solution that exists in the form of xylem. So xylem is the tissue that's responsible for transporting water and nutrients in plants. And structurally, it consists of these tubes that have sealed ends, but have perforations along the walls. And these perforations act as pathways for the water to travel from the root to the leaves. If we zoom into the structure of these pores further, then we see that these pores have a size scale of a few hundred nanometers, depending upon the tree species. So here are SEM images of some of the very commonly available conifers like eastern white pine, cedar, and ginkgo. And the sizes of these are in the size range of like 200 to 500 nanometers, which is way smaller than the length scale of bacteria and protozoa that are present in water. So the question that we are trying to ask here is that, can we use this naturally available membrane-like material in order to remove microbial contaminants from water? So our initial proof of concept experiments were pretty simple. So what we did was just take a piece of branch from a tree, and we peeled off the bark and pressurized water through it with the help of a nitrogen gas cylinder. And we were able to remove 99.99% of E. coli by using this simple method. So now we have been trying to develop these filters for household water, drinking water applications, and that involves a couple of more steps. But nevertheless, the method of fabricating xylem filters is very simple. So you take a piece of branch, you soak it in hot water for about an hour, and then you soak it in ethanol, and that's it, and the filter is ready for use. And I can explain more about the details of this process at the poster session. So now these filters can be operated under gravity. They don't require any kind of utilities. And you can adjust the flow rates by simply tuning the filter area and also the pressure. And so the filter here, so this is what a filter looks like. It's approximately 4 centimeters, and it's like just a 1/4 inch in thickness. So how do these filters perform? So the performance varies greatly with water quality. If the water does not have a lot of organic and dust content, then you can easily filter up to 72 liters of water at flow rates at peak flow rates of about 9 liters an hour. But if there is high organic and dust contamination, then the filter capacity is limited to 10 liters. So what we are basically looking at here is a filter that can be replaced on a weekly basis for household water applications and can be used on a need basis. So in order to prolong filter lifetime, you can use very inexpensive pre-filtration methods like cloth or activated carbon. And with this, you can achieve like a 2x improvement in capacity. So for water with high organic and dust contamination, you can still go up to a lifetime of about a week. In addition to laboratory studies, we have been conducting field tests in Uttarakhand in India. And the reason why we are working here is Uttarakhand is in the Himalayan region, and it has a wide variety of conifers that are available. Plus, the local people drink water from natural springs, which are prone to microbial contamination. And through our field tests, we found that 8 of the 9 filters that we tested were able to completely remove bacteria from this naturally occurring spring water. In terms of total capacity, we also tested these filters with groundwater, which accounts for 80%, 85% of the water used in India. And we were able to filter about 100 liters at consistent flow rates of about 2 liters per hour. And we were also able to demonstrate simultaneous removal of bacteria. And we have also been conducting user preference studies in order to understand what the user needs are to guide product design and development. And we found that, especially in the lower income households, there is a high preference for more frequent but less expensive replacement methods. So what are the key advantages of the Xylem filters? Well, first of all, there is a lot of flexibility that's available in design. In its simplest configuration, the filter can just have a plastic bag at the top and one at the bottom for pouring and collecting water. But there can be more advanced versions where the entire filter is integrated with a pre-filtration module. Second, there is also flexibility in terms of where you source the wood from. So first, you can also simply extract it from a branch, which gives a circular filter, or you can also extract it from the trunk, which is more convenient from a size standardization perspective. And so there is also flexibility in terms of manufacturing methods. So we have not patented this technology, and it could be either taken up by one large single entity, or it could also be taken up by several local entrepreneurs. And we plan to make this, the protocol for Xylem filter fabrication openly available. And the final, probably the most important advantage is the lower recurring cost. So one can think of it as a sachet version of a shampoo bottle. So as opposed to a filter cartridge that costs probably $8 and runs for 6 months, you can have a filter that costs about 8 cents but lasts for about a week. In the context of India, so this is a map that shows the cartridge recurring cost of the current membrane-based filtration technologies, and you can see that everything that's currently available is upward of 400 INR, while Xylem filters cost an order of magnitude lower, which is like 15 to 20 INR. The final advantage is also in terms of scalability. So there is a huge presence of conifers all across the globe, which opens up the possibility of several local manufacturing units. And in terms of a comparison of how much wood it actually takes to make these filters, the global softwood timber trade is about 121 million meter cube. But in order to make 1 million filters, you only really need like 12 meter cube of the softwood. And the other big thing is that these filters are made from the peripheral sapwood, which is usually a waste product in terms of the timber market. It's the wood at the core, which has a higher mechanical strength that's of great value. So we are effectively using something that's currently being discarded in the timber market. And here's the final conclusion. So we have been able to, so these filters can completely remove bacteria. The capacity depends really on the water quality, and you can process greater than 10 liters per hour. And the expected filter lifetime is of a few days, is of the order of a few days. And the filter cartridge is expected to cost somewhere like 10 to 50 rupees, which is like 5 to 10 cents. And you don't really require any kind of electricity to operate these filters, and they can be simply gravity driven. So with that, I'd like to thank all the people who made this project possible, and also to our funding sponsors, JWorks and MIT Data Center, and also Ferry Junior Fund that supported the project in its initial phases. Thank you.